So, Enviro Expert is pleased to introduce Randy St. Germain, President of Dakota Technologies. He developed much of Dakota's underlying time-resolved laser-induced fluorescence technology while pursuing a master's in analytical chemistry degree at North Dakota State University from 1987 to 1991. Randy and his colleagues have developed a continually improving series of direct push deployable site characterization systems for high-definition delineation of petroleum, coal tar, and creosote NAPLs in the subsurface. From early research field trials of laser-induced fluorescence at Air Force bases in 1992 through subsequent commercialization of the UVOST, TARGOS, and the new LNAPL system for chlorinated DNAPLs, Randy has spent the last 25 years characterizing NAPL bodies with laser-induced fluorescence. The title of the presentation is Laser-Induced Fluorescence Screening Tools 101, High-Resolution Site Characterization Technology. Randy, the platform is yours.
Okay, thanks. Thanks, Lowell. I'm getting an echo, maybe from you, Lowell. I'm not sure. Anyway, let's start out with a little bit of humor. Let's take a look at some really poor models. And these are poor models of animals. And everybody gets a chuckle out of them. And at one point I asked myself why that is, and that's because everybody knows what the real animals look like. Even if you hadn't ever seen a real polar bear, you got a pretty good idea that that's not a polar bear face. So we deal with conceptual site models of NAPL. And that's not so funny when your NAPL conceptual site model or your NAPL body is horribly wrong. And that's what I've been doing for many, many years. And over and over and over again, we see how monitoring wells are holes in the ground that lie to us. And unless we do highly spaced sampling and things like that, we're going to constantly be getting our NAPL body conceptual site model wrong. So I'm going to tell you today about a technology called laser-induced fluorescence. I've been practicing that particular science for about 30 years. It's a great tool for conceptual site models of NAPL bodies. So I'm going to describe what it is. I'm not going to do a bunch of case studies. I'm going to really focus on the technology. So if you should decide to use it someday, you're going to be extremely dangerous with that data. And of course, you can always call me. But you're going to know to some degree exactly what you're looking at. So I'm going to tell you when you should use it, and just as importantly for us is when you should not. We do not want to show up at a site and do LIF where it's not going to be a benefit for you. And so we're really pretty cautious about making sure that that it's going to be a benefit. And so we'll guide you in that whenever you send us samples or call us to visit about it. I'm going to tell you which flavor of LIF one should use. There's actually more flavor than one. And then I'm going to briefly, we'll cover a few topics of how you interpret that data. It's a lot just to get you up to speed on what this stuff is without analyzing a whole bunch of data, but we'll take a look at some of it. So let's talk about fluorescence in general. And here you have a picture of some crude oil in a jar of sandy soil and some diesel. The diesel doesn't really make itself visible very well. Down here, you've actually got these samples in a dark room, and we're using a mineral lamp to excite the fluorescence. And you can see that the diesel's fluorescing this beautiful azure blue, and the crude oil is kind of a white orange. The camera doesn't do a really good job. But that's what LIF does, or fluorescence itself. It makes things that aren't real obvious pretty darn obvious. LIF is not for the vadose zone. There's plenty of vadose. If we opened up those jars and put our little nose down in the jar, we'd smell plenty of contaminant in the vadose, and there's certainly plenty of contamination down in the water, in the saturated zone of that jar. But LIF is not for dissolve phase, and it's not for vadose. It's for the NAPL. So what's really going on here? Well, we've got a mineral lamp, a UV source of some sort, and it's constantly emitting ultraviolet light that our eye can't see, and the camera can't see it either, and that's why the soil looks black. But the PAHs that are in the NAPL, they are constantly being energized or excited by that UV lamp, and they're randomly expelling photons to get rid of that energy and get back to the ground state. And that's what polycyclic aromatic hydrocarbons are famous for. So what we've done with LIF is we built a sapphire windowed probe. And instead of looking through the side of a jar, we just take that jar, that transparent wall basically, and slide it down through the soil in real time. And we're using fiber optics to send laser light down and to collect fluorescence and bring it back up. And the goal then is to get those same kind of observations, but in a continuous format. Many, many, many measurements as that probe is being advanced at a steady speed down into the ground. And our hope then is to log the fluorescent nature of those NAPLs as the probe, direct push probe of some sort, is being driven into the ground. A log like this, you know, if it's 30, 40 feet deep, might just take a half hour or maybe even just 20 minutes, you know, from calibration to withdrawal. So it's pretty speedy technology. The idea then, and one thing that stands out for us a little bit, is we generate these waveforms, and they're kind of a signature of what is the fluorescence like, and we're generating lots of them. And the idea is that we can march around the site pretty quickly, you know, not much time being elapsed, and get a real-time adaptive look at where that fluorescence is occurring under the ground. And of course, the holy grail is for us to tag all that with the geo coordinates and be able to develop this nice conceptual site model detailing exactly where that source term NAPL material is at your site. LIF is deployable under a wide variety of platforms and conditions, and that's, you know, part of the direct push, I guess, gold rush even 20 years ago, was that it's so flexible. You can have big cone penetrometer test rigs, either wheeled or track. You can have little geoprobes getting into corners. You can lash things onto small barges. You can lash drill rigs even onto very large barges and push with a traditional drill rig. And you can even crawl out on the ice if you're brave enough and probe through sediments during the cold season up in Duluth. The nice thing, another nice thing about LIF and other direct push technologies is it's all 100% recovery. We're not relying on trying to get cobbles or running sands and things like that up to the surface for measurement. So I'm going to focus pretty hard on the spectroscopy behind laser-induced fluorescence, and that's the nature of those aromatic molecules that do the fluorescing, as well as the non-aqueous phase liquids, the solvents and the other molecules that are in those NAPLs along with the aromatic molecules. Petroleum's probably our most famous NAPL, right? It's our most commonly spilled, and most of us have worked on a petroleum spill site of some sort. And we all know that gasoline or petroleum ranges from light gases all the way up through asphaltenes, the stuff that we glop onto gravel and pave roads with, right? And there's a whole suite of sizes and shapes, hundreds and hundreds and hundreds different sizes and shapes of molecules. Our technology focuses on just those polycyclic aromatic hydrocarbons. But these straight chain molecules also play a critical role, and they're sort of the fluid, or not truly a lubricant, but I think of them as a lubricant because they really help those PAHs do their thing. When you isolate PAHs and let them sorb onto soil all by themselves without actually being in a NAPL, they don't fluoresce very well. They end up transferring their energy to soil particles instead of fluorescing. Here's kind of a layman's view of oil. It's every size and shape you can think of, and for us, we're just hoping, our technology relies on the fact that there's some aromatic or circular or ring-shaped compounds in there that we're going to target. Most of them are benign and don't play an actual active role other than make a nice suitable environment for that fluorescence to take place. And here's a short list of our target molecules. And things like gasoline don't have a lot of these in them, but they don't take very much of a highly fluorescent molecule like polycyclic aromatic hydrocarbons to fluoresce brightly enough that we can still track light hydrocarbons like gasolines using fluorescence, even though they classically don't seem like a big source of PAHs. One trend that we're going to have to keep in mind as we walk through this, and it's a pretty important trend, and that is the small PAHs, they fluoresce down in the UV, 2 rings such as naphthalene, and as they get larger and larger and larger, the absorbance and fluorescence that are required to observe these get longer and longer and actually even go out into the red. And even the fluorescent orange hunting jacket or the chartreuse fluorescent safety gear that we wear, those are all fluorescent molecules. And so fluorescence is all around us. We just don't use it all that often or so obviously. One thing that makes us stand out, and been at it for 30 years, is this is a time-based fluorescence technique. And here's the short of it. A bright laser flash happens almost like the strobe light at the disco and just instantaneously pours a lot of excitation energy out the front of that laser. That pulse actually takes time for it to go through the fiber optics, down through the rod string, and down into the ground and actually exit. So that takes about 3 or 4 billionths of a second. And then there's a phenomenon that happens just outside the window, a lot of scattering, fluorescing, everything else, and that's why it's colored white in this diagram, is because that represents all colors. Remember Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. All the colors together make white. Then another fiber optic captures that and brings it back up to the machine to point 3. And so we get a portion of whatever happened in front of the window arrives at the instrument. And here's sort of our key technology. Our instrument resolves that white light into 4 channels of fluorescence. And not only how intense it is at 4 key wavelengths, but also what's the decay time or the dying away of that fluorescence. And I'm going to explain that a little more in detail here. The whole time the machine is making many of those measurements a second, the geoprobe or cone penetrometer or even the drill rig is slowly advancing this down into the subsurface, and we're using a string pot and monitoring exactly how deep that probe is with time. And of course, a PC is logging all that information in real time. So if you have a machine, and we've built them over the years here at DTI, that measures all the different wavelengths and all the different decay times at those different wavelengths, you can actually build a little 3D model of the fluorescent nature of diesel, for instance, in this case. And our machine converts that complex information into waveforms, and that's the key for us, is this 2-dimensional data that we call a waveform, a multi-wavelength waveform. And here's a waveform for diesel, and diesel's tell, or its signature, is that it has a short lifetime in the first channel and longer lifetimes in the subsequent channels. And I've got a little animation here. I don't know how well it's going to play, but you'll notice that blue color is fluorescing, decaying away much faster than this cyan color. And that's kind of the idea you have to have in your head, is the decay of the blue channel is much more rapid than the subsequent channels. And that's the tell for diesel. So a NAPL's PAH content affects its fluorescence, its color, its intensity, its decay rate, right? So the behavior of the NAPLs is highly related to the nature of the NAPL itself. So here's a diagram where we have solvent molecules, being aliphatics and alcohols and everything else that's not playing an active role, over the PAHs. And so gasolines and kerosenes, they're kind of meh on the fluorescence scale because they're kind of pH starved. There's not a lot of active players. Crude oil and diesels, on the other hand, they're perfect. They've got a lot of active players in a perfect environment, so the ratio's just right. You get into coal tars and creosotes that are way too pH rich. They have almost nothing but actors and no stage. In fact, they all start stealing each other's lines. One corny analogy that I use, but it seems to work for people, is what we used to call water ballet. I think it's called the term escapes me now, but synchronized swimming or something like that. But this is sort of the gasoline. It just doesn't have enough players to do the thing. This is more like crude oils and diesels, perfect number of players, perfect amount of water. And then this is coal tars and creosotes. You've got way too many active players for any fun to go on. And so really crude oils and diesels are shooting fish in a barrel for LIF. And the others, they have their challenges, but we work around them. So I'm going to tell you about 3 flavors of LIF. One being UVOST. Because these NAPLs vary, you need different flavors. So UVOST is for the fuels and oils, you know, your classic refinery, filling stations, things like that. TARGOS is much more keyed for coal tars, creosotes, bunkers, and what we call heavies, and I'll describe that for you in a minute. And then I'm going to briefly tell you at the end about something called DieLife, and that's for molecules that don't actually inherently, or compounds that don't contain PAHs, so they don't inherently fluoresce, and we have to coax them into fluorescing by using a dye. And so I'll tell you about that after a bit. So let's dive right into UVOST. It's appropriate for all refined fuels up through heavy crudes. And so all your classics, gasoline, there's an exception, and that's aviation gasoline. There's something about aviation gasoline that it's quite devoid of any PAHs, whereas traditional gasolines usually have enough for us to use it on that. Kerosene, jet, diesel, crude, natural gas condensates are kind of a famous mighty fluorescer. And there are many, many other types of petroleum hydrocarbon that fluoresce just fine with UVOST. So here's a gasoline release example over in Minnesota, not too far from North Dakota. And you can see that we've got a couple axes here. One is %RE. I'm going to actually describe that in a moment. And then this one is depth. Where was the probe while the fluorescent measurements were being made? And these are called callouts. These boxes over here on the left-hand side, those are made by somebody selecting which waveforms, or if you see a bold line right along the edge here, that means that the average of all of these waveforms are actually shown there. And so let's take a look at this and see what we can see at a gas station. So the probe advanced, made hundreds of measurements, and then the computer actually converted these two-dimensional data sets into just single values called signal %RE. And like I said, I'll describe RE here in a second for you. But just it's basically how bright was the fluorescence with depth. Okay. We notice a couple things on this log, and one is that there's a darker blue color here than this washed out yellow or green, and hopefully you folks can see that at home. But you also know the waveforms. You see that the waveforms indeed were also different. And that's why those colors are different, is we're using the actual waveforms at each of those depths to color the data. And so a very blue or intact gasoline signal. This is the naphthalene channel, so we can tell it's quite intact as a gasoline. The computer figures out how much blue, green, orange, and red, swirls them all up together, and ends up coming up with a computerized color based on that much blue, green, orange, and red. And the same for these other waveforms, these other zones. You'll see the color intensities of the 4 channels change, so the resulting mixed up finger paint colors change, and that's how that color coding works. is when we see lots of different colors with depth, we know we've either got lots of different types of NAPL or a NAPL that has undergone various amounts of weathering. Another thing that we observe in LIF logs is the geology. When we see tight bristles, incredible changes in intensity over very short distances, that is screaming heterogeneity. And in fact, we were so impressed with this location, we went down and we cored, and we actually found little seams of sugar white sand in between clay, and this is in a glacial till area. Now, not too far away from that was actually another log that shows much more weathering, much more consistent with the weathered gasoline waveform, and not as tight of geology as well. I told you I was going to tell you about the RE, and that's how we calibrate, and that's we use a reference emitter, and that's a reference material, and then with UVOST it's a cuvette of oil. With TARGOS it's a gray fluorescent paint. And so all of the subsequent measurements that are being shown in these logs are all relative to how brightly those reference emitters fluoresced. So if you have something, for instance, let's look at that log that we just discussed, that gasoline log at a former gas station. It peaked out. There was 1 inch of data that in one little spot, it went through a little seam of sand that fluoresced 90%, right? As intense as that cuvette that we placed on the probe right before we did the hole. On average, it was probably averaging right in that 10% zone. And you can see a natural RE is going to be maybe 400 millivolts tall, 300. The waveform from the log is about 20, or maybe a tenth as high, roughly. And so that's how the RE works. And so every log basically you can just think is how bright was the fuel fluorescing in the pore spaces. And of course this is depth. And these are call outs that can be made of the many hundreds of waveforms that are actually stored in a log. Let's talk a little bit about heterogeneity. We see it all the time when we do LIF. We developed what are called butterfly plots, and these are just co-located LIF borings or logs that were conducted a foot apart. And at some sites we get really good consistency. We move over a few feet and we get almost the exact same log. At other sites, or the same site in a different area, we'll get quite drastically different results based on where we probe. And that's because we don't really know. We tend to think that things are laying in layers down there. All the time we get into layer thought. But in reality, at a lot of sites, tills and things, that fuel might just get pushed wherever it could by the pressure of a tank or something like that. You've got as much vertical distribution as you do horizontal. And by happenstance, this LIF event went through some NAPL and this other one missed it. So you just don't know. It's some sites are very homogeneous. It's a nice pregnant floating pancake, just like in the textbooks. But I'd say most sites we see perching, we see trapping. It's rarely a nice floating pancake on the groundwater surface. Another thing about gasoline is it varies tremendously due to weathering. And why is that? Well, a couple things. It's starting out low on PAHs when it was refined. It's kind of starved a little bit. And it's very volatile. And those smaller PAHs are readily lost due to weathering. Those blue channel PAHs are the first to go. In fact, I've got a little demo here for you. Here we mixed up some moist sandy soil with maybe 50% pore saturation gasoline, and I left it to weather. In other words, I tipped the lid open on the jar and just started to measure it once a week. And so here's the intact gasoline. A lot of intact gasolines right out of the pump would be strongest in the blue, but that can vary depending on if it's raw or if it's come out of a synthetic process or something. So this one happened to be weaker in the blue than in the green and the orange, but that's just how it came out, right? So fresh gasoline, and a week later, that gasoline is starting to weather because the blue channel, the smaller PAHs, are starting to evaporate, the naphthalenes and things like that. And as time goes by, that blue or red shifting, we call it, shifting towards the red, just keeps getting more and more intense. And so that's one of the problems with gasoline, is that it can weather and start to look like other products. For instance, this is a former gasoline station in Minnesota in 2010. And you can see that there is a big response at 7 feet there. Well, what is that? Is that motor oil? That maybe, you know, it was a service station? Was it hydraulic lift? It's got that sort of generic oil look to it. Well, actually, I suspect that it was weathered, highly weathered gasoline. And in fact, my theory is that gasoline can actually condense as it loses its volatile solvent properties. It's actually condensing down almost like condensed milk and just becoming a thicker, syrupy version of the original gasoline, and it's concentrating those PAHs. Down here, we have intact gasoline. There's no doubt about it. In fact, at this site, they have recovered gasoline out of some wells where the signature is blue, and they've run it in lawnmowers, in old lawnmowers, just for kicks. So that's one of the mysteries or challenges of gasoline, is it's gonna be a chameleon and it can look like a lot of other things. And you're gonna have to use other lines of evidence to kind of put together the conceptual site model of how to interpret these different weathering looking waveforms and colors. Lifetimes play a key role in all flavors of LIF, and let's delve into that while we're on the subject of weathering and even false positives and other types of advanced analysis we can do. They all rely on lifetimes. And here we've got a log where we see that just from the color alone, hey, there's 3 different distinct types of fluorescence happening in here. What gives? Well, let's just look at it. Type 1 waveform up on the top. You seem to have a distinctly different type of waveform in the middle. And at the bottom, we've got a type 3. And the computer code that we write is actually able to go through and analyze and look at the height or the overall intensity of each of those 4 channels, and it calculates that decay time of all 4 of those different channels. And what do we do with that information? Well, we actually spray. So when the software runs through that, makes all those calculations for all those depths, it actually sprays them, in a sense, onto a clustering diagram. And on this axis, you've got the wavelength. The more blue shifted waveforms like this are going to end up over here. And the more red shifted waveforms are going to end up here. And on the vertical axis, that has to do with those lifetimes. You'll notice these lifetimes are shorter than these. And we actually take a look at different channels and ratioing the different channels to get as much of a spread between the different types of fluorescence that we can. I suspect that at this site, this is all gasoline in various states of weathering. These surface gasolines are probably allowed to weather better than this buried deep. This, in fact, looks maybe trapped in some sort of big lens or feature of some sort. Why do I think that they're all the same? Is because we almost have a perfect beltway or continuum. A lot of times, if it's a completely separate product, we're going to end up off in space in a different dimension. But this is all running, and now this is starting to throw a little bit of a hint of diesel, but I'm not exactly sure how to interpret that. In fact, here is one of those clustering diagrams. If you take a bunch of different fuels, which we did, run them on a UVOST probe, and then do a clustering analysis of all those waveforms that were conducted in that 20-minute exercise or however long it took us, and spray them onto a clustering diagram, then you can see where the different types of products land. JP4 or jet fuel, for instance, is down here in the corner. Gasoline's kind of right in the middle, and as gasoline weathers, it's actually going to do a little bit of a walk up here towards the heavier compounds because it's literally turning into a heavier compound. Diesel's always way up at the top. In fact, that's how we designed this particular diagram, is to create as much spread for diesel because it's unique. Short, long, long, long. Remember that. And that's what brings it up on this vertical axis. And then coal tars and bunkers and like refinery number 5 and things like that, they're going to be very red shifted. Whenever you see a red shifted short lifetime waveform on a UVOST, you better be thinking, aha, it's a heavy type of NAPL, and it's probably dramatically underreporting the presence of that. I'll discuss that in a moment. So the take-home message for gasoline is UVOST detects it up until it literally weathers down into dirt and you really don't have much NAPL left anymore. Sometimes that gasoline is condensed. Its PAHs, like condensed milk, and a modestly weathered gasoline can fluoresce even more brightly than fresh. But it red shifts, and that's what allows us to tell when that's happening or not. And then dark clays, silts, and fines are optical reflection sinks. They negatively affect weak fluorophores like gasoline. So with gasoline, we're a little starved. We detect it a lot. It works just fine, but on a few sites where there's been a really dark clay or something like that and modest amounts of gasoline, we really struggle to detect it, and I'm going to explain why here. Why do fine soils cause a drop in fluorescence? Well, it's all about optics. So here's a sapphire window on a steel plate that we use to just basically do lab samples of soils and cores and things like that. Here's a jar sitting on top of that sapphire window, and the green laser is actually exiting that window and shooting up through space, but the clean water doesn't reflect it. You see just a little tiny bit of green light up here, but you're like, well, I can't really tell what's going on. But if I add a few little scattering crystals, right, to that vial, bang, you see that laser beam traveling up through that water. What happens if I throw some dirty soil with some fines into that jar? Well, here's some actually. First, let's look at clean sand, and you can see lots and lots of diffraction and scattering, and if there was NAPL in this sand, there would be lots of fluorescence along with that. So these are nice washed quartz sand grains. But if you throw dirty soil in there, bang, your eye can't see it anymore because all those fine particles absorb that light. If I wash that soil out, dink, right back to us being able to observe that optical phenomenon. And of course, everything is happening truly from underneath. Just in front of that sapphire window is where our system is making observations, not from outside the window like we're making observations in these photos. Let's practice a little bit about making the call. You're out in the field, you've got some gasoline field logs, and you're getting little nibbles. These big, strong hits, no doubt about it. Yep, this matches gasoline. In fact, it's oxygen-depleted gasoline with these really long lifetimes. But there's this little head scratcher up here. What is that? Is that a hit? Is that gasoline? Well, that's when you start relying on other things, like what's an adjacent log? Maybe an adjacent log also had gasoline up in that area, right? Next door, 10 feet away, you had this. Well, then I'm going to say, yep, that's a hit. There's no doubt about it because I'm seeing hits here. This little mystery blip, not quite strong enough. It's showing a little weathering. It's kind of hard to say. Again, once it gets really weak and small, basically staining of gasoline, that's when you have to sort of dig out other lines of evidence to help you understand one particular log. You know, at sites, it's showing some extreme NAPL saturation here. And again, this log indicates you've got some very tight structures that are holding that gasoline. Now, if an adjacent, another thing to think about, if you're wondering, oh, is this a false positive, is if at a lot of sites, maybe there's a natural mineral fluorescence. And over again, every clean log has this little bump right here. Well, then after a while, and you could go down and sample, of course, and figure out, oh, okay, there's a layer of shell hash or limestone fill or something that was causing that little baby false positive. So you can't analyze this stuff in a vacuum without looking at other logs. Here's another one. Is that a hit? Don't know. It's got the weathered gasoline, but that it could be a limestone or something like that. But what if we hung up a transect across the site, and ooh, look at that. It appears that the NAPL is rolling down some feature. And so then, instead of me wondering about it, I would be pretty conclusive that, yep, that's the toe of that NAPL just ending in that location. Here's an example of jet and kerosene. And jet's tail is almost total blue channel or 350 nanometer dominance, and that's because of naphthalene. In fact, this is a waveform from naphthalene, which, as you can see, matches the naphthalene waveform of that jet kerosene. Jet and kerosene, when they're refined, it's totally dominated by naphthalenes and methylnaphthalenes in relationship to other PAHs. Here's diesel. One thing about, again, heterogeneity. Look at that spiky, dramatic behavior with depth. It's got the short and then long lifetimes. And another tell for diesel is that it's the same top to bottom. This whole NAPL body, there's no weathering signs, there's no change. Even little tiny responses are the same as the very bright responses, and that means it's not weathering. In the diesel, we don't see much weathering behavior at all. So how does fluorescence change with NAPL saturation? We talked a little bit about that, but in general, if we were to do a calibration curve like we did here with diesel, and we spike varying amounts of clean soil with ever increasing amounts of diesel, and we put it on a UVOST system, here's the gasoline, and then you've got 100 ppm, 1,000, 110,000, and 100,000 ppm. And you can see in this scale, I scaled all of the waveforms to what that very high concentration of diesel, and you can see the waveform just got taller and taller and taller. In the field, we don't actually, we let those waveforms auto range, because even if I get a little tiny hit of just a staining of diesel, I want to be able to see that waveform and go, aha, that's a diesel waveform. It's a hit. If it was in fact, this is Fisher Scientific Sea Sand. That's the waveform for just plain sand. But we zoom in on that fluorescence behavior. And so literally you're just filling more and more and more pore spaces, and that fluorescence is just getting brighter and brighter and brighter because it's filling more of the voids between the soil particles. And they're getting deeper. Those void fills are getting deeper filled. Here's crude oil. UVOST is plenty good on crude oil. And here's an example of a kitchen sink. It's a bulk storage site. Are they different products, or are they all gasoline in various stages of weathering? I don't really know on this one, and I don't remember the specifics or if anybody ever bothered to find out. What we do know is we've got tremendous variation. This is very akin. In fact, there are no natural products we've ever run into. Wood debris, shell hash, peat moss, anything like that that fluoresces extremely blue shifted like that. This could be modestly weathered gasoline. It could be some diesel or some other mid-range product. This could all be crude, I have no idea, or highly weathered. Now you start getting into 400% RE, I don't think it's a weathered gasoline. So it's probably just a location that has a long history and many different products that are commingled, along with perhaps some gasoline that's under various amounts of weathering. So I'm going to shift gears quick. I'm going to talk about tar-specific green optical screening tool, or TARGOS, and that's visible LIF that we designed for heavies like coal tars, creosotes, and bunker fuel. Because UV LIF or UVOST struggles to respond well to those, and sometimes it struggles mightily, and I'm going to demonstrate that. And why? But why is that? Well, up in this top panel is my cartoon of a light hydrocarbon. And what's not pictured here is the alkanes or the straight chain molecules and all the other kitchen sink molecules that are in between the few PAHs, right? And they're spaced far enough apart that they can't literally hand energy off to each other. So you get UV light to come in and excite naphthalene fluorescence. He'll go into the excited state, that naphthalene molecule, and he'll fluoresce unperturbed. What happens in these heaviers in the middle panel is UV light comes in, might excite naphthalene, but that naphthalene can literally hand it off to larger molecules. And that larger molecule might in turn hand it off again. And at the end, you might get some red shifted fluorescence, but every one of those handoffs is fraught with the likelihood of a fumble where that energy is just converted into thermal energy. The way we overcame that with TARGOS was that we skipped right through the naphthalenes and we excite the very large molecules all by themselves. And in the quantum world, the big guys can't hand the energy back to the smaller PAHs. So it's a much more efficient process, and we do end up getting a better yield of fluorescence to excitation. So to demonstrate the problem or the struggles with UVOST is here's some coal tar, and it's a stubborn coal tar. It's pretty thick, goopy. And here we clean sand, 1,000 ppm, 10,000, 100,000 by weight of coal tar on that clean sand. And you can see that with UVOST, we start out with clean sand. We get the clean sand waveform. We put a little bit of coal tar on. Okay, yeah, things are going good. It's increasing in fluorescence, right? But look what happens as we add increasing amounts of coal tar. The signal actually turns around, non-monotonic behavior, and goes right back to where we started. That's a disaster for a screening tool, because we'd be focused on this area as being the most contaminated, and we'd be likely to ignore this when that is actually pure coal tar. So we don't want to do that. We don't want to use a tool that responds monotonically with concentration even to stubborn coal tars, and that's what TARGOS does. Increasing concentration means increasing fluorescence. And here, just to demonstrate, our UVOST and TARGOS log that were acquired side by side at an MJP site. You've got a pretty good mass of coal tar down here, and the UVOST is just whistling past the graveyard. It's giving some hints because it's got this incredibly short lifetime. That also indicates that energy transfer, that quenching mechanism is sort of running wild. It's also running wild with TARGOS. Very short lifetimes. Those are sort of the hallmark of creosotes and coal tars, is very short lifetimes because of that quenching mechanism of basically they're playing a game of hot potato and they all want that energy. Here's TARGOS on a crude oil release. And you may notice that the waveform is somewhat different. Again, lifetime plays a role. Your eye isn't used to looking at differences probably, but those are long lifetimes for TARGOS. And it's relatively blue shifted, we would call it. Okay, and we can run TARGOS off barges and water bodies, things like that. So, but again, those lifetimes play a role, which channels they're fluorescing, and of course all that gets converted into colors, so you can see different colors with depth. We do know that this NAPL is pretty homogeneous, this whole mass, and the same with this. In fact, these two are a match. This type of NAPL at this location is the same as the type of NAPL at that location, the same waveform, same fill colors. So we've done more than 375 coal tar or creosote wood treater sites. Former manufactured gas plants are a lot of our TARGOS projects. Here's just as an example, we did 188 TARGOS logs at this big wood treater. Looks like a mess, but in actuality, 92% of the site soil that we screened was void of significant NAPL, at least using our fluorescent technique. And the validation sampling demonstrated that pretty well. Even at one site, the logs can obviously vary tremendously because the nature and the type of distribution of the, you've got drip yards and other places where this creosote has been released over time, different geologies that it's traveling through. So anywhere from, boy, you got creosote top to bottom, to whoa, out here on the edges where it's falling down. Remember, creosote and coal tar are DNAPLs. They can go deep. And a lot of times we're chasing it down to depths, and then we're finding those seams, those transport seams of creosote and coal tar. Again, we've got clustering diagrams that can help put the pictures together of all the different types of fluorescence. You've got diesel on a TARGOS. That's the diesel waveform, relatively long lifetimes and very blue shifted. Modest heavy oils, they've still got a long lifetime, and then you get into the coal tars and creosotes and they really start to shorten up. Those peaks get extremely narrow, and that's kind of the tell that we use. We also can use these same charts for finding shell hash or differentiating peat moss or something, or wood debris and things like that. So we're constantly using these lifetime spectral combination lifetimes and clustering diagrams and something called non-negative least squares fitting to try to filter all that out and make sense of it. I'm going to move on, I guess, to the last flavor, and that's called dye life. And early on in the discovery, how did a high-resolution site characterization come into vogue for the dissolve phase? That was almost all driven by folks who were exploring or trying to figure out how chlorinated DNAPLs, how that contaminant was behaving in the subsurface. And they were driven insane by the fact that every year they would go back and they'd seem to get different results. What they eventually discovered, and only with high-resolution screening tools, was that 90% of the transport and storage and things were happening in 10% of the soil. Only when they went in at very high resolution, this is actually dissolve phase work, and the folks at Guelph are kind of famous for this type of work. But then they found that there were these transport highways. Not all the soil is the same. You've got coarser and finer. You've got movement in some areas, storage in others. And it was only when they got those high resolution tools that they understood, oh, well, no wonder we got different results. You only move over a few feet each year, and bang, you're going to get a different answer. Tools like the Waterloo advanced profiling system, the membrane interface probe, they've revolutionized people's ability to understand that complex architecture. But for the NAPL itself, that source term material, those tools are inadequate. And so what most researchers went to was to harvest soils out of cores at very high resolution and then do these oil red O or Sudan 4 shake tests. And so that was a way of them knowing, do you truly have source term NAPL, true non-aqueous phase liquid? Now, of course, we've been chasing DNAPLs, coal tars and creosotes, with TARGOS many, many years. And so a couple guys, Adrian Fury and Murray Anderson from Haley and Aldrich, they proposed a few years back that we get on our horses and ride for a dye technique. And he convinced us to do that. And dye life was born. And here's how it works. So you've got DNAPL ganglia. This is a little cartoon, right? In soil. And the idea behind dye life is that as the probe is being steadily advanced into the formation, we're forming this snail's trail of a dye. And it's a hydrophobic dye that doesn't fluoresce when it's in contact with soil. But in areas where it actually makes contact with DNAPL, it blue shifts its fluorescence and its fluorescent lifetime increases dramatically. In fact, here's a couple examples of what that indicator dye looks like when it's just in soil. And here's the indicator dye, much more intense and blue shifted and longer lifetimes where it contacts those NAPL ganglia or pools. And the result then, of course, is to filter the data and look for those two different types of responses and end up with a very high resolution log. And here's a picture of that dye being emitted from a port down below the sapphire window. We recently did a demo. You can learn all about it on the Dye Life page of our website. But here's a kind of a typical log, 215,000 discrete laser shots. Every 64 shots were averaged, so we did 3,660 waveforms in every log down to 60 feet, or roughly so. Running a little short on time, I'm gonna step it up a little bit. There are so many data points in here that there aren't enough pixels on the screen. And so there are actually probably hits in here that we can't see because the one little response we got isn't even a pixel in width on a computer screen. And so we recently did a demo, well, I guess not so recently now, maybe 4 years ago now, but these are the different type of UVOST, and everywhere that you see blue, there's a pool of DNAPL, of chlorinated solvent, TCE in this case. And so we use those waveforms. They play a key role. We can get disturbed sand has a certain waveform, NAPL in contact with the dye being injected itself. We can later go in and process those and filter them out. In fact, while we're injecting the dye, in fact, we've got HP or hydraulic profiling capabilities with all our tools now. But as that dye or just plain water is being injected, we're also doing permeability measurements. But these are little tiny hits that you see down there, and you don't really get to see them stick out until you process that same log. And we have to post-process them every 5 feet because the resolution of the tool is so high. We don't want to miss even pea-sized or BB-sized ganglion of this DNAPL. And here, as an example, here's just the dye waveform at this depth. But right here, that waveform's got just a little bit of elongation of the lifetime in that first channel down there. And that sticks out like a sore thumb to us because that means that there was some NAPL there. And if you use your imagination, you can tell that this waveform is actually mostly undissolved dye with a little bit of dissolved dye signature thrown in. And these are just photos of the validation sampling that went in, and just to basically demonstrate how quickly you can be in NAPL and then back out. This area is screaming high in dissolve phase, I can promise you that, but it doesn't have true non-aqueous phase liquid or source torn material. Real quick, I guess the standout feature for me of Dye Life is that you get about over 10,000 of these oil red O shake test equivalents each day, all with 100% recovery. That probe stays in the ground. The sampling went very, very difficultly at that site. In the demo, you can read all about it, but it wasn't easy to get cores out of the ground because of running sands. With Dye Life, we were able to log all the time, top to bottom. And Dye Life data is really challenging our 3D visual community. So thanks for attending. I'm going to close down. Just want to mention we offer free NAPL analysis. If you've got NAPL in wells and ditches and recovery systems and you're wondering about using LIF, send us some and we'll do free analysis. And I also offer free data interpretation. If you've got UVOST data, TARGOS, Dye Life, any kind of data, and you've got questions about it, you get a hold of me via email or something like that, and I will certainly help you out. And that ends my presentation.